All right, let's dive straight in. Today on the Depth Dive, we're tackling a really fundamental challenge in the world of LM agents, which is just exploding right now. How do we actually get these, increasingly smart AI things to talk to each other, and not just each other, but the rest of the digital world too? We've got this fascinating paper here, a survey of AI agent protocols. Seems like it might be the first really comprehensive look at this whole area.
Absolutely, and it's hitting a core bottleneck.
Yeah.
We're seeing these incredibly capable LLM agents pop up, doing all sorts of tasks. But the fact that there aren't agreed upon ways for them to communicate, that's starting to really hold things back. It's kind of like having, brilliant scientists who can't share notes because they all use different, totally incompatible systems. This survey gives us a much-needed map of the territory.
Okay, so for everyone tuning in, let's get right to the key insights. What's the gist? Basically, this paper hammers home the urgent need for standard communication methods now that LLM agents are becoming so common. It gives us this really smart, two-dimensional way to sort through all the existing protocols out there, compares them on stuff that really matters, like, security, how well they scale up. And crucially, it looks ahead. What's next? How do we get more adaptable, more collaborative agent systems? So yeah, if you're deep in the weeds of AI research or even just trying to get the big picture, this survey seems packed with vital info.
Yeah, definitely. And for the researchers and engineers listening, the paper offers some pretty solid contributions. Just that classification framework alone, splitting protocols into context-oriented, which is about getting info, versus interagent, which is about talking to each other that brings much-needed structure, and then breaking those down further into general purpose and domain-specific. That adds another really helpful layer of clarity to a field that feels, well, a bit fragmented right now.
And it's not just putting things in boxes, right? The paper actually evaluates them, conceptually at least. Looks at how efficient they are, scalability, security features, things like that. Plus, a big chunk on where the research needs to go next. Sounds like required reading. Okay, let's dig into that classification framework then. That feels like the foundation for everything else.
Agreed. So that first dimension, context-oriented versus interagent. Let's start with context-oriented. What are these protocols actually for? Okay, context-oriented protocols are fundamentally about how an LLM agent gets the info it needs from the outside world. Think databases, APIs, web services, other tools.
Right.
If an agent needs to pull up the latest stock price or translate something, these protocols define how it asks for and gets that external context.
And the paper's point is that not having standards here is causing problems. Friction.
Exactly. Big problems. Without standard ways of doing this, you see a lot of fragmentation. Different LLM platforms have their own ways of calling tools. Prompts need to be written differently. And the folks providing the data or services, they offer up their resources through all sorts of different incompatible interfaces. It just puts a huge burden on developers. They have to become experts on loads of different systems. It kills interoperability and drives up development time and cost.
Right, like trying to invent a universal TV remote when every TV uses a different signal.
Okay.
So within these context-oriented protocols, there are general purpose and domain-specific ones. Let's start general. The paper flags Anthropic's MCP. What's the deal with MCP?
MCP, yeah, the Model Context Protocol. It's really being put forward as a foundational piece. Anthropic's aiming for a universal open standard. The idea is any LLM agent could use MCP to talk to pretty much any external resource, data, tools, services in one consistent way. It's basically trying to build that standard pathway for agents to get the external info they need to do their jobs.
Okay, so how does it work in practice? What are the moving parts?
The paper breaks it down into four main components. First, the host, that's the LLM agent itself, the brains figuring out what info is needed. Then there's the client. It sits with the host, knows what resources are available, and actually puts together and sends the request. The request goes to the server, which acts like a middleman to the final piece, the resource, the actual database, API, whatever. The server gets the info from the resource and sends it back to the client.
So a kind of structured request pipeline. What does an actual MCP interaction look like, step by step?
Yeah, it's a three-phase cycle. Starts with inference. The host LLM figures out, okay, I need this external context. Then the request phase. The client builds the specific MCP request and shoots it off to the right server. And finally, response. Server grabs the info from the resource, sends it back to the client, which passes it to the host LLM to use in its answer.
And the big win here is tackling that fragmentation mess we talked about.
Precisely. Because it's a public defined protocol, MCP sort of decouples how the LLM uses a tool from the tool's specific details. If everyone adopted MCP, LLM developers wouldn't have to custom build integrations for every single tool. Big boost for interoperability. And for the tool providers. One MCP integration makes their service available to potentially tons of agents. Lower costs, wider reach.
You mentioned security, too. There's a specific advantage there, isn't there?
Oh yeah, a crucial one. The paper makes a good point about how MCP improves security over, say, traditional function calling. In function calling, the LLM might generate the whole API call, potentially including sensitive stuff like user API keys. With MCP, the LLM just says what it needs. The local client handles the how building the actual API call, managing the authentication locally. This keeps sensitive credentials and data closer to home, reducing the risk of exposing them over the network.
That's a pretty compelling benefit. Okay, shifting slightly domain-specific, context-oriented protocols, the paper mentions agents.json. What's the focus there?
Right, agents.json. This comes from Wildcard AI. It's more focused. It's an open source format, machine readable, designed specifically to bridge existing web APIs, the ones websites already have, and AI agents. Think of it as a standard way for websites to say, hey, AI agents, here's how you can use our stuff in a way you understand, which is vital, because most useful data is already out there behind standard APIs.
So how does agents.json make those APIs easier for AIs to use?
It builds on OpenAPI, which is already a standard, but adds things specifically for AI. It introduces concepts like flows, which are like predefined recipes of API calls to get something done, and links, which show how data flows between different API steps. This helps the LLM understand and reliably manage more complex, multi-step interactions with the website services. It's designed to be stateless, require minimal changes to existing APIs, and be really easy for LLMs to process. It just clarifies how to interact, reducing the guesswork for the agent.
Okay, that makes a lot of sense for plugging agents into the web we already have. Let's switch gears now to the second main category, Interagent Protocols. Why do we need standard ways for agents to talk to each other?
Well, as these agents get smarter, we're realizing that for really complex jobs, one agent often isn't enough. You need a team. Multiple agents need to collaborate, share what they've found, coordinate their actions. Interagent protocols set the rules for that conversation, and the demand is growing fast. We want to overcome the limits of single agents, make things more efficient, maybe lower costs by splitting work, and build systems that are more robust if one part fails.
So what are the core things a good interagent protocol needs to handle?
The paper points out a few key challenges. First, just agent discovery. How does an agent even find another agent that can do what it needs? Then, information sharing. How do they pass data, results, intermediate thoughts back and forth effectively? And finally, you need those standardized communication methods. Common languages and interfaces so agents built by different people on different platforms can actually understand each other.
And just like before, these interagent protocols also split into general purpose and domain specific. Let's explore the general ones first. The paper lists quite a few.
Yes, it's a really interesting landscape emerging here. A&P, A2A, AITP, ACONP, ACOMP, Agora, quite a list. They all aim to help agents communicate, but they definitely have different design goals, different target scenarios, different technical foundations.
Let's zoom in on a couple. A&P, the Agent Network Protocol, sounds ambitious.
It really does. A&P is an open source effort, and its vision is massive. An internet of agents. Think a global, interconnected, secure network, potentially linking billions of agents doing all sorts of things. The core ideas are universal connection, using existing standards where possible, but enabling really seamless collaboration through things like automatic organization and negotiation between agents. It's very forward-looking, aiming for a truly open, decentralized system.
Wow, okay. That's a huge goal. How is it architected to even attempt that?
It's built in 3 layers. At the bottom, the identity and encrypted communication layer. This uses things like W3C decentralized identifiers, DIDs, for secure, trustless, encrypted links between agents. Above that is the meta protocol layer. This is really cool. It's like a protocol for protocols. It lets agents figure out and agree on which specific protocol they'll use for a particular chat. They even mention Agora, which we'll get to, as a way to do this negotiation using natural language. And at the top, the application protocol layer. This defines standard ways to do essential stuff like finding other agents, describing what they can do, and handling specific types of tasks.
And what does a typical A&P interaction look like?
It usually starts with discovery. An agent needs help, so it uses A&P's standard ways to find potential partners. Once it finds one, it grabs the agent's description file, says what it does, how to talk to it. Then, using the agreed-upon protocol from the meta layer, it starts the conversation, setting requests, handling authentication, and processing the replies.
Fascinating, like building the pipes for a future web of AI. Now, what about Google's A2A? How does that compare? What's its angle?
A2A, agent to agent. Google's approach here is maybe more immediately focused on the enterprise. The goal is seamless collaboration within organizations, even if they're using different AI tools from different vendors. It's about simplifying integration and providing core functions for discovering capabilities, negotiating how things work for the user, managing tasks and state, and keeping it all secure. So while A&P has that grand decentralized vision, A2A is more aimed at solving the practical problems companies face building multi-agent systems now.
And what are the design principles behind A2A?
Simplicity is key. They try to reuse existing web standards like HTTP, JSON RPC, service and events. It's definitely built for the enterprise. Robust authentication, authorization, security, observability are all baked in. It's async first, built around tasks and long-running workflows, which is crucial for real-world stuff. Modality agnostic, handles text, files, media, and it pushes for opaque execution. Agents don't need to spill their guts about how they work. Just focus on the context, state, instructions, and data being shared.
Okay, so what are the core building blocks within A2A, the main concepts?
The paper mentions a few key ones. The agent card, basically a JSON business card advertising capabilities. A task is a unit of work. Artifacts are the outputs or results. Messages are the basic chat units. And parts let you break down big messages or results.
And how does an A2A interaction typically play out?
An agent publishes its agent card to say, here's what I can do. The client agent finds that card, figures out it's the right agent for the job. The client then talks to the remote agent using the A2A protocol, kicking off a task. This might finish quickly or take a while. Eventually, the remote agent sends back the result as an artifact. The paper mentions it's already seeing some success in enterprise settings.
It's really interesting seeing these different takes on the same fundamental need. The paper also quickly mentions AITP, ACONP, ACOMP. Any key differences jump out?
Yeah, briefly. AITP from the near ecosystem emphasizes secure, auditable communication, especially using blockchain for decentralized stuff. ACONP from Cisco and LangChain is more about a standard interface for calling and configuring agents, simplifying how developers use them. And ACOMP from AI and data seems focused on practical features for agents that rely heavily on natural language and talking to external models.
Now, Agora gets special attention. What's unique about its approach to interagent communication?
Agora tackles what the authors call the agent communication trilemma head-on. This is the trade-off between versatility, efficiency, and portability. Basically, if you make a protocol super versatile, handle anything, gets complex, which hurts efficiency and makes it hard to implement everywhere, portability. If you optimize purely for efficiency, low overhead, you might limit flexibility. And making it easily portable often means keeping it simple, which can also limit versatility. It's a balancing act.
That's a really clear way to put it. So how does Agora try to solve this trilemma?
Agora's big idea is to use the LLMs themselves, leverage their ability to understand language, generate code, and negotiate. The core concept is that agents can adapt how they communicate based on the situation. For common stuff, use efficient structured protocols. For rare or complex things, maybe generate communication routines on the fly, or even just use natural language to figure things out or negotiate. A key part is protocol documents, PDs, plain text descriptions of protocols. Agents can use these to autonomously negotiate, implement, adapt, or even create new protocols without a human stepping in.
So it's much more dynamic, less fixed.
Exactly. By supporting different communication styles, prioritizing efficiency where needed, but keeping flexibility and letting agents manage protocols themselves, Agora aims for a better balance across that trilemma, especially in diverse networks.
We've covered a lot on general purpose protocols. Let's touch on the domain-specific interagent ones. These are tailored for particular fields, right?
That's right. The paper groups them into human-agent interaction, robot-agent interaction, and system-agent interaction, each focusing on the specific needs of those areas.
Okay, human agent first. PXP and LK are mentioned. What are they about?
PXP, the Predict and Explain protocol, focuses on making interactions between human experts and LLMs understandable, back and forth. It uses tags like ratify, refute, revise, reject within a structured flow. They use it in radiology and drug synthesis, places where clear justification is critical. OK layered orchestration for knowledgeful agents is broader. It's a decentralized framework tackling identity, accountability, ethics, and agent systems. It talks about using DDs for identity, having intent-focused communication, and even ethical consensus protocols. More of a whole ecosystem approach.
And for robot-agent interaction, CrowdES and spatial population protocols.
CrowdES is about generating realistic crowds for robots to navigate and interact with, using diffusion models for agent variety and Markov chains for movement. making simulations more believable. Spatial population protocols, or SPPs, deal with swarms of simple, anonymous robots figuring out where they are relative to each other just by pairwise chats, like asking, "How far are you?" Enables collective localization without a central map.
Finally, system agent protocols, LMOS, and agent protocol.
LMOS, Language Model Operating System, is an Eclipse project aiming for an internet of agents. It has layers for semantics like JSON-LD, transport negotiation, HTTP MQTT, and identity security, DIDs, OAuth2. It's a big framework vision. The agent protocol from AI Engineer Foundation is more focused. It's a standard for how control consoles talk to agents, defining concepts like runs, threads, and store for managing the agent's lifecycle, state, and memory.
Fascinating how specialized these are getting. The paper also hints at a convergence between interagent and context-oriented protocols. What's the idea there?
Yeah, it's an interesting thought. They suggest that maybe the line is blurring. When an agent uses a context-oriented protocol to call an external tool, you could see that tool as a simple, low-autonomy agent. Conversely, when complex agents collaborate using interagent protocols, you could view each agent as a highly specialized, high-autonomy tool. As autonomy and complexity grow on both sides, the distinction might become less meaningful. We might need more unified ways to think about these interactions.
That's a really interesting angle. Okay, the paper then shifts to evaluation. How do we compare these things? They make a good point that static comparisons get outdated fast. So the focus is on the dimensions for evaluation.
Exactly. They adapt 7 core metrics from the history of internet protocol development and apply them to LLM agent protocols. These are efficiency, scalability, security, reliability, extensibility, operability, and interoperability. It's a really solid framework for assessment.
Let's unpack a few. Efficiency, obviously key. What does that cover for agent protocols?
It's more than just network speed. It's throughput, latency, both network travel time and semantic processing time, handshake overhead, message size. And crucially for LLMs, the cost of semantic processing and token usage during communication counts too. Key metrics are things like latency figures, throughput, like task per second, header sizes, token counts, CP memory use.
Scalability vital if we imagine huge networks of agents. What are the key metrics there?
Scalability isn't just about handling more agents or links. It's also about how well the system handles discovering new agents and coordinating them as it grows. The paper looks at node scalability, performance as agent count grows, link scalability, performance as connections increase, and capability negotiation, how quickly and successfully agents can agree on protocols or tasks as the system scales. They even suggest a capability negotiation score.
Security non-negotiable, especially with autonomous agents. What are the main security aspects?
It's about trusted interactions, authentication, making sure agents are who they say they are, encryption, keeping chats private, integrity, ensuring messages aren't tampered with, and addressing unique challenges in decentralized semantic systems. Metrics include things like the variety of authentication methods supported, how fine-grained access controls are, and whether there are ways to desensitize or anonymize data in transit.
Reliability, we need these comms to actually work consistently. What's important here?
Reliability means stable, accurate communication. Mechanisms for guaranteed delivery, completeness, handling failures. Things like automatic retransmissions for lost packets, flow and congestion control to avoid overwhelming the network, persistent connections to reduce setup overhead. Metrics might include retry counts, convergence time for flow control, disconnection rates, message loss rates.
Extensibility protocols need to evolve without breaking everything. How's that measured?
Yeah, can it adapt? Key metrics are backward compatibility, can old versions still talk to new ones, flexibility, how easily can new features be added and tested, and having clear ways for customization and extension, like custom fields or plugins.
Operability sounds like the practical side. How easy is it to actually use the protocol?
Exactly. How easy to implement, manage, integrate. Metrics look at the number of dependency components, the size and complexity of the code. Lightweight is good. Deployment and configuration difficulty. Is it framework agnostic, well documented? And observability. Are there tools for monitoring and debugging?
And finally, interoperability. Can different systems actually talk using this protocol?
The ultimate goal for many standards. Can systems built by different teams on different platforms and different networks actually communicate seamlessly? Metrics include schema compatibility tests. Can they understand each other's data formats? Plus broader checks on cross-system, cross-browser, and cross-network adaptability.
That's a really thorough evaluation framework. The paper also uses case studies like MCP evolving and the shift to A&P A2A. What's the main takeaway from those?
They really show the evolution in action. MCP adding HTTP support and auth showed a move towards broader use and better security. The jump from MCP tool integration to A&P decentralized P2P and A2A enterprise collaboration highlights increasing complexity and specialization. The paper's advice based on this is sound. Choose protocols that fit your specific context, focus on security and performance early, and keep an eye on how these standards are constantly changing.
Okay, to make this even more concrete, the paper analyzes a use case, planning a 5-day trip from Beijing to New York using MCP, A2A, A&P, and Agora. Can you walk us through how each tackles it?
Yeah, it's a helpful comparison. MCP imagines one central travel agent LLM calling separate flight, hotel, and weather servers directly. Simple, controlled, but maybe inflexible potential bottleneck. A2A shows distributed intelligence. Specialized agents, transportation, accommodation, activities talking directly. The flight agent might query the weather agent itself. More flexible, more like real collaboration. A&P emphasizes cross-domain work. Agents from different organizations, airline, hotel co, weather service, interact via formal protocols across boundaries. Good for distinct capabilities and security needs. The flight agent formally negotiates with the weather agent. Agora shows a user-centric flow. The user's natural language request, plan my trip, gets translated by Agora's layers into standardized protocols for specialized agents. Hides complexity, very adaptable.
And the bottom line from comparing these is that there's no single best one. It depends entirely on the application's needs, like agent autonomy, communication complexity, required standardization.
Precisely. It's all about the context. What kind of agents doing what kind of tasks with what kind of interactions. That determines the best fit.
Okay, looking ahead. The paper has a whole section on the academic outlook, short, medium, long term. What's on the horizon soon, short term?
Short term, the push is towards more dynamic, adaptable protocols. Expect better benchmarks going beyond just task success to measure efficiency, robustness, adaptability, scalability. Privacy-preserving protocols will be huge, especially for sensitive data, maybe borrowing ideas from federated learning. The idea of an agent mesh protocol, like a group chat for agents with shared history, could improve coordination. And maybe the biggest shift, protocols becoming evolvable agents, learning to manage, combine, and refine how they communicate.
And midterm, a bit further out.
Midterm, maybe built-in protocol knowledge. LLMs trained with protocol info directly in their parameters, making interaction more seamless, though maybe less adaptable. Also, more layered protocol architectures, separating transport, semantics, task logic. Think TCP/IP layers, but for agents. This boosts modularity, scalability, maybe allows embedding ethical rules at higher layers.
And the really long-term vision, where could this all lead?
Long-term, it's thinking big. From protocols to intelligence infrastructure, exploring collective intelligence in massive agent populations, understanding the scaling laws governing these systems, and maybe developing dedicated agent data networks or ADNs infrastructure built for autonomous agent communication. Structured, intent-driven data exchange, supporting planning, persistent state, all without humans constantly in the loop.
That paints a really compelling, almost sci-fi picture of the future. So, wrapping up our deep dive, what are the absolute key takeaways from this survey of AI agent protocols?
I think the biggest thing is that this paper provides that crucial, first comprehensive look at a field that's moving incredibly fast. The key takeaways are: 1, the urgent need for standardization is real and growing. 2, the classification framework they propose is super helpful for understanding the landscape. 3, the evaluation dimensions give us a solid way to assess protocols. And 4, the future directions are fascinating, moving towards much more intelligent, adaptable, and collaborative agent ecosystems.
Yeah, it really feels like the evolution of these protocols could fundamentally change not just AI systems, but maybe distributed intelligence more broadly, how humans and machines work together, everything. It definitely makes you wonder what possibilities and challenges might come from a truly interconnected internet of agents. Lots to think about. Thanks for joining us for this deep dive. We'll catch you next time.